In this video, we will learn about Keto Enol Tautomerization. The word tautomerization refers to a type of isomerization specific to a situation where it's really easy to interconvert between two isomers of a given molecule. And so before getting into the actual keto enol tautomerization, I wanted to put this in a little bit of context. And so one of the things that we deal with when dealing with organic molecules is eventually biomolecules. So it turns out that living things have historically just evolved into using a specific enantiomer of many different molecules for all of the biochemistry that keeps us alive. So an example of this would be this amino acid right here. So this is aspartic acid. All of our amino acids will look like this, where we have an amine, a carbon, and a carboxylic acid, kind of an S stereocenter, and some sort of a group coming off of it. So the various different amino acids have a different group coming off here. So an observation that has been made in the past is that if you just look at someone who's alive and, I guess, extract their tooth and look at the stereochemistry of all the aspartic acid, you'd find that 100% of it will be the S enantiomer. Now, if you go and dig up a skeleton and look at the aspartic acid in kind of the preserved bone there in the tooth, what you find is that in a 350-year-old tooth, only 66% of that aspartic acid is going to be the S enantiomer. And so what that means is that there's got to be a chemical reaction happening that explains how we're going from having the S enantiomer to having at least a little bit of the R enantiomer. We'll get to a complete answer to this at the end of the video, but the beginning of the answer turns out to be explained by the fact that all carbonyls are able to interconvert or tautomerize between their keto form and an enol form. So this process right here that I'm showing would be the keto enol tautomerization. Again, the carbonyl side is the keto or ketone form, and what looks like the alkene is the alkenol, so enol, where the al comes from the alcohol, ene from the alkene, the enol form. This tautomerization generally should favor the carbonyl, and we explain that by saying that the carbon-oxygen double bond is much stronger than a carbon-carbon double bond. And so, for example, for a molecule of acetone, the equilibrium constant is 1 to the enol, 6600 or so to the keto form. As you might expect, the enol form is not always the disfavored tautomer. There's all sorts of factors that can swing that balance in the equilibrium. We'll look at some of those now. So the first of these is actually aromaticity. And this is actually really interesting because you probably never thought about it this way. But a phenol is actually the enol form of this carbonyl compound right here, where I'm looking at the enol that is drawn like so. As you can imagine, being aromatic is much more important than having a carbon-oxygen double bond. So this is a much more stable tautomer here. And that is indeed true. If you look at a bunch of molecules of phenol, only about 1 out of 10 to the 10 of them will be in the keto form. Something that enol forms can do a little bit more of compared to keto forms is hydrogen bonding. And so, for example, when you have a 1,3-dicarbonyl compound like this, it's actually the enol form that is favored. So in this case, the equilibrium is about 3 to 1. The reason is that in the enol form, we're able to get this nice cyclic hydrogen bonding motif right here, where the hydrogen bonding from the enol to the other carbonyl is adding a bunch of stabilization, and it's enough stabilization to be more important than having this carbonyl alone. Another thing that you might notice here is that by going to the enol form on one side, you actually get more conjugation, right? Because now we delocalize the carbonyl on the left with the enol, and that is indeed another factor. And so here's another example of how conjugation can stabilize an enol and lead to certain enols being favored over others. So in this case, the enol on the right is going to be less stable than the enol on the left, and probably the enol on the left is likely to be more important and more stable than the keto form. Another factor that we think about when thinking about the stability of alkenes is that the more substituted they are, the more stable they should be. And that is true here. So when we have more alkyl groups substituting an alkene, then that alkene is going to be more stable. And so what we would expect here is that the keto form would be the most stable tautomer. But between the two enols, we should go with the more substituted enol here as the one that's likely to be more stable. Finally, the solvent that the molecule is dissolved in is also going to affect the extent to which the keto and enol form are favored or disfavored. So going back to this 1,3-dicarbonyl compound, what I'm showing here is, again, the keto enol tautomerization, but noticing that the equilibrium constant actually depends on the solvent that the molecule is dissolved in. So when the molecule is dissolved in water, this equilibrium actually favors the left side, whereas when the molecule is dissolved in benzene as a solvent, the equilibrium favors the right side. And so this is a pretty interesting observation, and the reason for this difference is that in water, we can use water molecules to do hydrogen bonding to both of these carbonyls. And so because of that, then going to the enol form and gaining hydrogen bonding is not really that significant, right? Because there's always hydrogens around for the carbonyls to hydrogen bond to. So then being carbonyl is more important and more stabilizing influence. Moving to benzene as a solvent, however, now there is no hydrogen bonding contribution from the solvent molecules that are surrounding these molecules here. And so then, in order to get some of that stabilization from hydrogen bonding, the molecule is going to be more stable in its enol form. So, like all of organic chemistry, the context of the solvent that everything is dissolved in can influence the structure that you're actually dealing with. Keto enol tautomerization takes place through two different types of mechanisms. The first of these is base catalyzed. And so, for example, if I take this ketone right here and have some sodium hydroxide reacting with it, then I will kind of enable this equilibrium process. The mechanism looks like so. The key thing to recognize is that the hydrogen that is in the position that is alpha to the carbonyl, that hydrogen is acidic. So for a ketone, that pKa right there at the alpha position is about 20. And so it's acidic enough to do this deprotonation. So I'm going to come in and deprotonate and do what looks like an elimination or a beta elimination type of process. That gets us to this intermediate right here, which is not an enol because there's not a hydrogen yet attached to the oxygen. And as you can imagine then, an acid-base reaction in this direction should get us to the actual enol form. So looking at this mechanism, I think you can see how the process is catalytic in base because the base we started off with is recreated during the second acid-base step. And a second observation to make here is to look at the pKa's and decide whether or not this mechanism is going to happen to any appreciable extent. And so comparing our pKa's between our acid and our conjugate acid of the base, we see that the difference in pKa units is 4. So this reaction should really be in equilibrium favoring the left side, but not to the point that this can't happen. So some small amount of the time we're going to get this acid-base reaction happening, which can then cause the second acid-base reaction, which should be pretty much a 50-50 proposition because we're dealing with two different OHs as our acids that we would be comparing. And so if there's a base catalyzed version of this reaction, the tautomerization can also be acid catalyzed. And so here's the simple example of the exact same molecule under acidic conditions tautomerizing to the enol. The mechanism looks like this. So again, we have an acid. So what we should be doing is looking for whether or not we can protonate something. In this case, I gave you a pretty strong acid. So this is tosic acid with pKa of -3 or so. Protonating a carbonyl kind of makes sense here because a protonated carbonyl is going to have a pKa of -7. So a similar difference in pKa as I showed you up here. So the left side of this reaction or equilibrium would be favored a bit, but not to the point that this overall process can't happen. When you do protonate the carbonyl and get to this intermediate, then you can do that same beta elimination looking process. Deprotonate, getting you to the enol. So going back to the aspartic acid example that I brought up at the beginning, what's going on there? Well, something really important about keto enol tautomerization is that that process, which is just possible, is fighting against biology's urge to produce a single enantiomer. So what we're getting is a process that looks like so, where the amino acid here can sometimes undergo keto enol tautomerization to the enol form, And then when it goes back to the keto form, then it has two possibilities because we've made a planar carbon here. We've turned this stereocenter, which is an sp3 carbon, into this planar sp2 carbon. And so during that keto enol tautomerization back to the enol form, we can either protonate from behind to get back to the original enantiomer, or we can protonate from above the plane of the screen, getting us to the other enantiomer. Those should be 50-50 propositions, so given infinite time, any amino acid will eventually equilibrate to being a racemic mixture of enantiomers. And so you are probably used to thinking about chemistry as taking place on a time scale that maybe you could do within a lab period in class. But you should notice up here that I gave you a 350-year-old tooth in which only a small portion of the amino acids had racemized. And the reason for this is that when molecules are in solvent, that is very different from when molecules are in a solid state. When molecules are kind of packed together in the solid state, it might be a little bit harder for reactions to happen because you don't have molecules moving around and colliding in the correct orientations in order for a reaction to happen. In the solid, molecules are a little bit more fixed, so it's going to take a lot more time and random chance for any sort of molecular wiggling to even lead to any possible reaction. In a fossilized tooth or whatever type of fossilized object, there's just not going to be enough acid or base present to make the keto enol tautomerization take place at a significant rate. And so it's that situation that leads us to be able to use amino acid racemization as a way to date living things. Well, I guess dead things. That being said, it's also important to kind of keep in mind that on the previous slide I showed you how pKa's are a way to think about whether or not a keto enol tautomerization might be happening to an appreciable amount. While conversely, when you're in the solid state, those pKa's are also a little bit hard to work with because if a molecule happens to be packed right next to another molecule that has a basic site next to it, even though it's not the strongest base, just because physically they're so close to each other, it might be more possible than normal, predicted by pKa's at least, for an acid-base reaction to happen. So no matter what, if you take a biomolecule, whether it's dissolved in water or just kept as a solid, over time keto enol tautomerization will happen, and along with that racemization of stereocenters. In organic chemistry, this tautomerization is really important because we think of carbonyls themselves as being electrophiles. However, they can be tautomerized into the enol form, which is actually now a nucleophile because it's an alkene with an electron donating group attached.